Let's move on to our next speaker, John Percy from the University of Toronto. He'll talk to us about variable stars.
Okay, thank you very much. As some of you know, variable stars are the main interest that I've had in astronomy for something like 60 years. And it seemed to me that for a group of recreational astronomers, it would be appropriate to just remind you of how interesting and exciting variable stars are and how easy it is for you to observe them either for fun or to actually do real science. So I want to show you just a few examples of variable stars that are interesting for different reasons, and hoping that you will go out and actually observe these. And I just remembered I was supposed to tell you where I was. I'm in West Toronto under fairly muggy skies here. So here's an outline of some of the reasons and some of the things that I'm going to mention. A lot of the stars that you know and love turn out to be variable in brightness. This is part of their personality. It's also part of their physical behavior. A lot of these stars have interesting human interest stories behind them. And one of the reasons that I like astronomy is the human interest aspect of it. Astronomy isn't just done by textbooks or machines, it's done by real people. And of course, you can go out and observe variable stars for fun, for recreation, or even more remarkably, you can actually go out and observe variable stars to contribute to astronomical research. And I've been working for many, many years with skilled amateur astronomers, helping their observations to see the light of day and to contribute to science. And finally, variable stars are still on the frontiers of astronomy today, and I'm going to mention a few examples of that. Now, I'll flash this slide up at the end as well, but I just want to assure you that there's lots of resources to help you do this. The absolute best place to go for information about variable stars for people like you is the American Association of Variable Star Observers, which has existed for well over 100 years and is based in Cambridge, Massachusetts. Another thing that's very easy for you to refer to is the RASC Observer's Handbook. And there are several pages in the handbook which will provide you with a beginning of variable stars, simple charts to make observations, an explanation as to what kinds of variable stars there are, and one or two features on specific stars. Now, I can modestly say that the best place to go for a book, even though it's slightly out of date, is my book, Understanding Variable Stars, published by Cambridge University Press. You should be able to find it out there somewhere. It's available as an ebook as well as a hard copy. And finally, you may have noticed that in every issue of our journal, I have a column on something that interests me. And I've referred here to a recent column called Variable Stars I Have Known, and You Should Too. So do go to that article there. I'll mention some of the stars in this presentation, but there's a few others there that I can highly recommend. So let's start with the best known star in the night sky, at least for northern observers, and that's Polaris. But Polaris is more than just a star in the sky that happens to help us to find north or to find our latitude, but it isn't the brightest. One of the things that I give lectures on is misconceptions in astronomy. One of the great misconceptions is that Polaris is the brightest star in the night sky. Actually, it ranks number 47, but it's a triple star. The brightest star in the system is a white supergiant star, and it's a 3.969-day Cepheid pulsating variable star. And the graph at the bottom here shows the brightness of the star measured in magnitudes. This shows that the amount of variation is a huge 2%. So I don't advise you to go out and try and measure the variability of Polaris, particularly with your naked eye. It's hard enough to do with photoelectric photometry. But it's an extremely interesting star. One of the things that we can do with it, and this is one of the important tools of variable star astronomers, is something called O-C. Now, O is just the observed time of the maximum brightness of a variable star, such as Polaris, and C is the calculated time, assuming that we know the period and the period is constant. So we can calculate when the star should be at maximum, and we can calculate O-C. Now, if the star's period was constant, then O-C would always be 0, and we just get a straight line on this graph that you see here. But no, the graph is not a straight line. Indeed, it's very close to being a parabola. And a parabola occurs if the period of the star is slowly increasing. And the period increase can be very slow because the observed effects are cumulative. It's very much like having an error on your watch. It may only be a second a day, but after a few weeks or a few months, you can clearly tell that there's something wrong with your watch. So in the case of Polaris, the period is increasing by 4.5 seconds a day, seconds a year, sorry, and that is almost certainly due to the evolution of the star. The star is slowly getting larger. Larger objects vibrate more slowly. They have a longer period. And so we can actually observe this and test our models of stellar evolution. And we can do this for many other kinds of variable stars. But another remarkable thing about Polaris, and this is almost the only star that this occurred in, is that over the last century, the amplitude of variation has slowly decreased. So in this graph at the top here, that's the amount of variation in percent, decreasing from 10%, apparently on its way to 0 by the year 2000. Now, in fact, it didn't decrease to 0. It remained at 2 or 3%, as you can see from the rightmost points on this graph here. And this phenomenon was discovered by a graduate student, Armando Arellano, when he was a student working at the University of Toronto using the David Dunlap Observatory in Richmond Hill. Now he's one of Mexico's most distinguished astronomers, and we're very proud that he obtained his training here at the University of Toronto. So this is remarkable. We really haven't a good explanation as to why Polaris has done this. So it does have the potential of telling us something new about stellar physics. Now, the other reason that Polaris is extremely important is that it's an anchor for what we call the Levitt Law. The Levitt Law used to be called the period luminosity relation for Cepheid pulsating variable stars. And it was discovered by Henrietta Leavitt at the Harvard College Observatory. And she noticed that in the Magellanic Clouds, which are stars all at the same distance, the ones that had the shortest periods were less luminous. The ones that had the longest periods were more luminous. And so the graph on the right here shows that relation. And it can be calibrated if you know the periods and the luminosities of a few Cepheids. And in particular, if there's Cepheids that are near enough so that you can use the parallax method in order to determine their distance. And so because Polaris is so close, you would have thought that it was a very good candidate for calibrating this law. But strangely enough, until only a few years ago, the distance of Polaris was quite uncertain. There were some astronomers who thought it was about 330 parsecs, others who thought it was more like 440. And now we know through the Gaia satellite that the distance is the latter. It's 445 parsecs. And so this allows us to confidently use Polaris as an anchor for this very important relation. Because using the period luminosity relation, if you observe a very distant Cepheid but can measure its period, then you can assume its luminosity and from its apparent brightness, use the inverse square law of distance to determine what its distance is. And this is one of the cornerstones of modern cosmology. Well, I mentioned that Polaris was not a very good star for you to start observing. One of the best ones, if not the best one, is Delta Cephei, which is the Cepheid variable that actually gave these stars their name. So here we see a photograph of the little corner of the constellation Cepheus, which, as you know, looks like a house. And there's this little triangle of 3 stars in the corner of it, Zeta at 3.6 and Epsilon at 4.2. And your job is to estimate what's the brightness of Delta in the upper left here relative to Zeta and Epsilon, whose magnitudes are known and are given on this chart here. Now, what people tend to ask at this point is, well, what's the answer supposed to be? And I have to point out that, well, that's for you to figure out. This is science. You're making a real observation. So do go out with a star like this and get started. Now, you might wonder if I actually went out and made these measurements and submitted them to the AAVSO, then what use would be made of them? I'm just taking one example here from my latest column in the RASC journal, which is on the death of the sun. In the previous presentation mentioned the case of planetary nebulae, which represent the what happens after the sun casts off its outer layers and turns into a white dwarf. Well, when the sun undergoes this transformation, its size is decreasing, so its period should be decreasing. And so the star AV Cygni, and that's a typical variable star name, has been observed for almost a century by the AAVSO, and we can use a technique called wavelet analysis, which actually fits a sine curve to the different parts of the light curve, the graph of brightness versus time, and estimates at each point what the best period is. And that's what's shown in the red curve on this graph here. And the black line is a linear fit to that curve there. And it shows that the period of AV Cygni is slowly decreasing. And over the course of a few thousand years, perhaps represents the fact that AV Cygni is transforming from yellow giant star, which it is now, to a white dwarf and a planetary nebula. So this curve here is based on thousands and thousands of visual measurements made by skilled amateur astronomers through the AAVSO. And this is one of the kinds of science we do. This was a project done by a 4th-year student working with me last year through our work study program. And we've just posted this as a paper, and we will probably submit it to the journal of the AAVSO, which is how we try and feed back this sort of work to the observers who actually make the observations. Now, you've probably heard a little bit about Betelgeuse recently and its so-called great dimming, which is shown at the end of this graph here. This is a graph of the magnitude versus Julian date. And these are all photoelectric observations here. Now, the claim really is that there's something strangely unusual about the dimming of Betelgeuse. But actually, when we take a century of observations, visual observations, photoelectric observations, what we learn from this is that Betelgeuse varies on 2 time scales, 390 days and about 2,000 days. And both of these variations have variable amplitudes. And it turns out that at the time of the Great Dimming, a year or so ago, both of those variations were at the minimum in their cycles, and both of them had their amplitudes at the maximum. And so adding these 2 things together produced this unusual fading of this star here. But the point here is that if you want to understand what a star is doing, it's often useful to look at the history of this star. And so what I've told you here is based on a century of observations by skilled amateur astronomers for the AAVSO. And from that, we can deduce what the different timescales and behaviors of Betelgeuse is. Here's another good star to start observing, Algol. There's a chart of Algol in the Observer's Handbook, and it's an eclipsing variable star. And for a few hours, it fades quite noticeably. So one observation that everybody can do is go out, look at the constellation Perseus, and simply ask, well, is Algol at minimum or is it at normal brightness, where it's about the same brightness as the other stars in the constellation? Remarkably, it turns out that Algol and its period were apparently known to the Egyptians 3,000 or 4,000 years ago. A paper got submitted to the Astrophysical Journal, and I was asked to see if I could recommend someone to try and referee this paper because the claims seemed to be quite remarkable. But when it was carefully reviewed, refereed by expert astronomers, they actually believed that for whatever reason, the ancient Egyptians observed Algol and observed its eclipses. The fact that its name means ghoul or the demon star or something like that also suggests that Islamic astronomers knew about its eclipses too. But at least in modern times, John Goodricke is given the credit for suggesting that the variability might be due to eclipses. He also was the one who discovered the variability of Delta Cephei. And remarkably, he did all these things in his tragically short life of only 21 years. But at least by the time he died, he was a fellow of the Royal Society. So he was recognized, and he was an amateur astronomer. He and his next door neighbor, Pigott, did a lot of interesting things in terms of the beginnings of variable star astronomy. Now here's another star whose chart is in the Observer's Handbook here. This is Mira in the constellation Cetus. It's the prototype of pulsating red giants. And it's interesting that its variability was actually discovered in 1596, which means that its variability was discovered before Galileo's important work providing a proof for the Copernican hypothesis for how the solar system was laid out. And of course, the two supernovae discovered by Tycho in 1577, the one discovered by Kepler in 1604, these also predate most of Galileo's work. And they suggested that despite what Aristotle said, the stars were not always perfect, not always unchangeable. And so in this sense, the stars helped to overthrow the Earth-centered model of the universe. It was not just solar system phenomena that supported Copernicus and overthrew the Ptolemaic system. Okay, quickly a few frontiers of how variable stars figure in modern astronomy. You've probably heard of pulsars. They're rapidly spinning neutron stars being formed in the collapse of stars, massive stars at the end of their lives. And in this set of images here, we see how the brightness of the pulsar, which is this star here towards the very center, varies over the course of the variation, which is only 1/30th of a second. The Crab pulsar pulses 30 times every second. Now, one interesting thing is that apparently the human eye can see this flickering in a sufficiently large telescope under sufficiently good conditions. And I've wondered perhaps whether the DDO 74-inch is large enough where you might be able to see this on a reasonably clear night, or whether our skies are simply too bad to observe something like this. By the way, if you want to get involved in this, the AAVSO has a high energy section, and they make observations that are relevant to things like neutron stars, black holes, white dwarfs, and other high energy phenomena in astrophysics. I mentioned supernovae. Supernovae are still very, very important in modern astronomy. I hope you've all heard of supernova 1987A, discovered independently by our own Ian Shelton at the top here, but also by amateur astronomer Albert Jones, probably the most remarkable variable star observer ever. He's made over 500,000 He made over 500,000 measurements during his lifetime and was referred to as the man with photoelectric eyes. So here's an example of a light curve here of a supernova. These observations coming from skilled amateur astronomers. Amateur astronomers discover supernovae as well as measuring them. And supernovae are now one of the other keys to the cosmic distance scale, along with the Cepheid pulsating variable stars, because their peak luminosity is very close to being constant. And so we can use them as lighthouses, as it were, for very distant objects. Certainly one of the great frontiers is exoplanets. One of the remarkable things, I think, is that the nearest other star to the sun, which is Proxima Centauri, not only has exoplanets, but one of them is Earth-like in the sense that the temperature would allow water to exist as a liquid, which is probably a prerequisite for life. Now, unfortunately, particularly Earth-like exoplanets, if they transit across the face of their star, produce only a slight dimming. So here's a graph here showing the dimming of this star because of its exoplanet, and it's only about 0.005 magnitude. So it's about 0.5%. But amateur astronomers can contribute to exoplanet research. The AAVSO has an exoplanet section. So if you go to this address here, you can find out how you, with a CCD camera, can contribute to modern research on exoplanets. I want to finish up with a couple of examples of some recent work that's been done by my colleagues. And this is Maria Drought. She's actually my next door neighbor in the Astro building at U of T here. And she was of note because she led the team which produced really the birth of multi-messenger astronomy. Now, you may have heard of multi-wavelength astronomy, where you look at cosmic objects at different wavelengths, from radio to X-ray to gamma rays, and with all the ones in between. And that's been done for many decades. Multi-messenger astronomy now occurs when we can obtain signals from gravitational wave bursts. And a gravitational wave burst was observed 2 or 3 years ago. Previous to that time, gravitational waves bursts could not be localized because there were only 2 active observatories, and that was insufficient to triangulate. But when a third and to some extent a fourth gravitational wave observatory were able to measure the burst, it was possible to approximately localize this burst. And so Maria and other teams went out looking for it, and indeed her team won. At the bottom here, you see this very faint object here, which is coincident with the burst. And it turns out to be the in-spiral and merger of 2 neutron stars, producing a huge burst of gravitational waves when they merge together. Now, it turns out that this phenomenon is very important because it seems that this is how most of the elements in the universe heavier than iron are formed. It was previously thought that they were all formed in supernova explosions, but this is not only an important development in instrumentation and observation, but also in our understanding of a fundamental part of astrophysics. So again, there's a link here to the press story. And finally, and this is even more recent here, in one of my columns last year, I talked about ASSASSIN, which is what we call the all-sky automated survey for supernovae, ASAS-SN. And this is a huge database. It has huge amounts of information in it. In fact, this is one of the databases that my students are now using to study variable stars, because there's of the order of 2,000 days of intense observations of something like 500,000 variable stars. Now, Anna O'Grady, who is one of our graduate students, was actually looking, data mining the ASSASSIN database for strange objects called Thorne-Dikov objects which are hypothetical red giants which have acquired a neutron star core. She didn't definitely find any of those, but what she did find was a whole new population of stars called super asymptotic giant branch stars. So these are stars that are even more luminous than red giants being the phase that the sun will go through and towards the very end of its life. So again, there's a link here to a press story here. And if you want to do some of this kind of stuff yourself, there's actually one of the Zooniverse projects for you to work on. I hope you're all familiar with Zooniverse. It sort of started with the Galaxy Zoo project, in which you were to classify images of galaxies. Well, in this case, the Assassin team has called on your help in classifying some of these 500,000 variable stars from their light curves. And I might point out that one of my students last year has found out that at least for pulsating red giants, about two-thirds of all the Assassin classifications and analyses are incorrect. So there's actually a huge amount of work done here. So if you see that, if you refer to that JRAS column that I mentioned on the previous slide there, it has some ideas and the appropriate web links if you want to decide on cloudy nights to do data analysis and data mining from the Assassin database or from the AAVSO database or whatever. There's very good software available, a package called VStar, which is what my students use for this, for doing analyses of this kind. So I'll end simply by putting up this list of resources here that reminds you that if you're interested in variable stars and want to start observing them, there's lots of places that you can go for information. So thank you very much. If you got some questions, I'd be happy to try and answer them. Thank you.
Thank you very much, John. Always a pleasure to have you present to us. Let's go to Emma. Do we have any questions for John?
We do. The first question comes in from Lewis. Is Beetlejuice really a variable star?
It is a very variable star, yes. There's absolutely no question that Beetlejuice is a variable star. This is its light curve. It varies by something like 1.5 magnitudes and in a very complicated way. No question that it's variable.
Thank you. Question 2 also comes in from Lewis. Can our sun be classified as a variable star because of changes that occur in its activity, especially as related to flare activity?
Definitely so. The sun is a variable star in several different ways. If you remember the previous presentation, the images of the sun with sunspots, as sunspots rotate around the sun, then the sun varies slightly in brightness with the same period as it rotates, which is about 30 days roughly. It also varies, as you mentioned, because it flares. It could be observed as a star with exoplanets. Many of you have observed the transit of Venus and transits of Mercury. You know that when a planet transits across the disk of the sun, its brightness presumably decreases by 1% or so. And so it's variable in that way. And it also is a very low level pulsating star in a very complex sort of way. So it's 4 different kinds of variable stars.
Thank you. Andy wants to know, with sky surveys doing a lot of the data gathering, what are the best types of variables for amateurs to observe?
I could say that almost any kind of variable star is still worthy of observation. And the good thing about having the AAVSO is that with its team of scientific advisors, it can suggest specific projects on specific kinds of variable stars that you can do. So I, for instance, am one of the scientific advisors for the long period variable section, which observes things like Mira stars, but there's the exoplanet section, the high energy section, there's a solar section, et cetera, et cetera. And so they can recommend the kind of measurements that are particularly useful. And then there's all this data mining stuff. There's all this stuff in these databases here, which is either incompletely analyzed or the analyses are incomplete or incorrect, as I and my student found them to be for the red giant stars. So there's still lots to be done.
That's all of our questions. Thank you.
Oh, thank you. And by the way, this is my 60th year of Toronto Centre membership, so I'm very pleased to be with you tonight.
Very good. How many years, John?
60.
60.
I joined in 1961.
Wow. I thought I heard 60. I just want to make sure. That's an awful long time. Congrats.
I have a column coming up in the journal on that.
Fantastic. Thanks again for your presentation, John.
My pleasure.